Hello, Alberto here. Thank you very much for clicking on this video. Before I talk to you about how do we perform a simultaneous search for multiple transition pathways, let me first clarify what we mean by high-dimensional free energy landscapes. In the context of computational chemistry, we typically represent this sort of free energy profile where you can see an unstable state A and unstable state B that are separated by a free energy difference and a free energy barrier between them. Now, in reality, there are very few systems that can be represented by such a one-dimensional reaction coordinate, but luckily we can go up to 2 dimensions where we can still represent a free energy surface with valleys and mountains in between. In the same manner, we can extend the concept to 3 dimensions where now you see free energy isosurfaces that separate the stable states. Now, the weakness of this approach is not only that it becomes less interpretable, also, as we increase the reaction coordinate dimensionality or the number of collective variables, the computational cost of getting this sort of free energy landscapes scales exponentially. And that's why, since some years ago in our group, we have been working on methods to circumvent this issue. And in particular, we have been coming up with adaptive path frameworks in which, rather than exploring this, for example, 2-dimensional space, what we do is that we draw a path between 2 known states, and we explore the progress along this adaptive path at the same time that we optimize it to follow a minimum free energy route connecting the 2 states. We can do the same in 3 dimensions, where you can see here how we draw a path and then adapt it to find an optimum route in this space. Now, because the progress along the path is a 1-dimensional coordinate, then we can recover a free energy profile along this path that shows you, again, the free energy difference between the states and also the free energy barrier. Here you can see the same for the 3-dimensional system. And during my PhD, I've been working in these kind of methods, mainly known as path metadynamics, together with several collaborators to study many systems, among them, for example, acid dissociation, enzyme catalysis, and very recently, together with Professor Karma Rovira, the deactivation of a blue light sensing protein. And if you want to test this method, then you can do it in the Plume library. But today, rather than talking to you about applications, I would first like to spend some time talking about method development, and in particular, how do we exploit parallelism in our path metadynamics framework. Because first we started with a single walker path metadynamics, where we have basically one simulation exploring the path from A to B. Then if we introduce parallelism, we can have multiple replicas, that is multiple simulations that all explore the same path and the same free energy from A to B. But then we introduced a new level of parallelism where now we have multiple pathways, each of them with multiple walkers that explore different routes. So first, let's talk about the simplest version of the method, the single walker path metadynamics. Here you can see again the 2-dimensional system, which in this case is alanine and peptide. We are going to the equatorial to the axial state. And here you can see how we start sampling along the path, and we optimize it according to the sampled average density, which is an indicator of the free energy gradient. You can see how the path converges to a low free energy route between the 2 states, and at the same time we calculate the free energy profile along this path. Now, for the multiple walker example, I'm going to show you a 3-dimensional system. The 3 collective variables are the omega angles of a polyproline chain. And in this case, we're going to use 8 walkers. So here you can see the 8 walkers, all of them exploring the same path and represented in different colors. And you see how after some time, they all agree on a particular mechanism that in this case is a zipper-like mechanism. First omega 1, then omega 2, and then omega 3. And you can see here the barriers corresponding to the rotation of each of the residues. But now, what if we wanted to explore more pathways? Let's go back to the alanine dipeptide to show you how multiple path metadynamics works. So here you see again the equatorial and the axial state. And before, we were able to recover one minimum free energy pathway for this transition. Now, if I initialize 2 pathways, then in principle, I should only be able to get the same answer twice. So both pathways would converge to the same result again. But if I induce repulsion between the pathways, then we can force one of them to find an alternative route. So here you can see how the purple pathway recovers, again, the mechanism that we observed before, but the green one is forced to find an alternative route. And if we look at the free energy barriers, then indeed you can observe how the barrier for the purple mechanism is slightly lower than the one for the green mechanism. Now, what are the limits of our method? If you think about the polyproline case again, when we found the omega-1, omega-2, and omega-3 pathway, then in principle, this could also happen in other orders, right? So you could have, for example, omega-3, omega-2, and omega-1, and in total, there are 6 possible combinations. And our multiple path metadynamics framework is actually able to capture these 6 different paths that in this case basically look like the edges of a cube. And now I could in principle show you the one-dimensional free energy profile of each of these 6 paths. But rather than that, we have been working on an alternative way to see the free energy when we have this sort of multiple pathways. And this is what we call the path map. And here we introduce 2 new collective variables. One of them is S bar, that is basically a weighted average of the progress along all of the paths that is weighted based on the proximity to each of them. And the other one is set bar, that is basically an indexing of the paths that is also weighted according to the proximity to each of them. So for example, when you are in a set var value of 1, then this means that you are mostly close to path number 1. But when you are in a set var value of 3.5, then this means that you are mostly at a point that is equally close to all of the paths, which is what you see at the stable states. They are marked by S bar values 0 and 1. So basically, this is the PP1 state and this is the PP2 state, where you can see these values. And then as you go forward in the transition, then you can see how first the paths do a trifurcation. And then when you get to the middle of the transition, S.5, then you can see how each of the pathways bifurcates again. So you have here the 6 possible pathways. And then they start to merge again until they arrive to the next stable state. And it's very nice here that you can see all the free energy features for all the 6 possible pathways in a simple 2-dimensional representation. And if I show you the projection of the free energy along the S-bar coordinate, then we recover again the 3 free energy barriers that you saw before. Now, today, I also wanted to show you an application of this multiple path framework on something else than peptides. So for that, we chose this system that we have been working on together with Jocelyn Fede, David Svensson, and Professor Peter Bolhaus, where we study the transition from what you see here, that is a Watson-Crick-Franklin base pairing DNA. And we observe how it rotates or rolls and arrives to this alternative base pairing state that is known as Hochstein. And this rotation can happen, as you saw it here, within the confines of the double helix, or it can also occur first by flipping the adenine outside of the double helix. It rotates once it's outside, and then it comes back already in the Hochstein state. So to do that, we are using 2 cyclic paths. One for the inside pathway that you see here is basically the purple one. And because it's a cyclic pathway, it starts in Watson-Crick-Franklin, it rotates to Hochstein, and then it rotates again to Watson-Crick-Franklin. And in this case, we are only moving through what we call the base rolling angle, which is basically a measure of this rotation of the adenine. And then we have another pathway that is the one that happens outside of the double helix, that is represented in green, where you can see how at the same time that we are moving in the base rolling coordinate, we also open in the base flipping coordinate towards the major group of the DNA. So then our intermediate state looks like this with the adenine flipped out. And with this framework, because we have extra efficiency based on our path strategy, then we can treat multiple different sequences of DNA. We have one reference sequence, which is the only one that had been studied before, A6DNA. And in order to study sequence dependence, what we do is that we change the neighbor in the 5' direction, which is originally a C, for the 3 other possible nucleotides. And then we do the same for the original A neighbor in the 3' direction. With our multipath framework, we efficiently get the outside and the inside pathways for each of these sequences, as well as the free energy profiles. Here you can see the results for the 5' variations, as well as the original sequence. And here you can see the results for the 3' variations. There are some patterns that I would like to highlight in this data. The first of all is the fact that when the adenine rotates with its 6th ring in the 5' direction of DNA, the free energy barrier of the process is consistently higher than that of the rotation in the 3' direction. And this has to do with the relative length of the sequence in each of the directions of the DNA. Another aspect that we wanted to study was the stacking. So we monitored the distance between the two neighbors of A16, the A and the C in the original sequence. And we noticed that for the outside pathways, this distance is mostly undisturbed during the transition, while for the inside pathways, this distance increases for the intermediate state, as it has to accommodate for the rotation of the adenine. And we see that the free energy barrier high increases only slightly with the distance between the neighbors for the rotation in the 3' direction, while for the rotation in the 5' direction, the increase is much steeper for the free energy barrier. Now you might be wondering if all of these parameters that we're studying, including our collective variables, are good enough for this DNA system. And this is a question that we addressed together with Pérez using genetic algorithms and neural networks to select collective variables that can best predict the atomic coordinates of a molecular system. And for our DNA, it turned out that indeed the base rolling and base flipping angle, together with some other distances, are the best at predicting the intermediate configurations of the DNA. Here you can observe how the neural network reconstructs the base rolling with the adenine rotating within the double helix. And here you can observe how it also can reconstruct the flipping outside of the double helix. And with that, I will just like to thank first my supervisor, Brent Ensing, our collaborator, Jocelyn Frede, for the DNA work, Ferry Hoft for the work on CV selection, and all of you for your attention.